Challenge, let us start the class. Bismillahirrahmanirrahim. Our lecture title is Zener diodes and applications, and this is lecture number 8. In this lecture, we will discuss Zener diodes, the construction of a Zener diode, the characteristics of Zener diodes, the properties of Zener diodes, and the various applications of Zener diodes. And in this diagram that is available on the first slide, the practical Zener diode itself and the symbolic representation. This slide presents the introduction to Zener diodes. And I will read from the slide that the Zener diodes, or breakdown diodes as they are sometimes referred to, are basically the same as the standard PN junction diode, but they are specially designed to have a low and specified reverse breakdown voltage. And in a while we will see what is this reverse breakdown voltage. The impurities in the P and N material of the Zener diode can so be adjusted so that the reverse breakdown voltage, or also called the Zener voltage, can be controlled as desired. So the Zener diode is a simple diode with one extra feature, that is the breakdown or the reverse breakdown voltage or the Zener voltage can be controlled by controlling the impurities that are doped in the P and N material of the Zener diode. Zener diodes are used in applications such as voltage references or also in voltage regulators. And in this diagram, we see the symbolic representation and the practical available Zener diode. It consists of two terminals. One terminal is called the cathode terminal and the second terminal is called the anode terminal. Now, looking at the practical diode, how do we identify which terminal is the cathode and which terminal is the anode? Well, on every practical diode, we will see a black colored strip or a colored strip that is facing to one, or which is tending or which is directed to one terminal. This strip will not be available in the center. It will be available either towards one terminal. And this terminal that the strip is located near to will always be the cathode terminal. Since there are only two terminals, the cathode and the anode, the strip, the black colored strip, will define the location of the cathode terminal, and the remaining terminal will be our anode terminal. And the second diagram that we see is the symbolic representation of the Zener diode. It is slightly different from our usual simple diode. The arrow in the symbol represents the anode terminal, and this straight line represents the cathode terminal. Now, next is the voltage current characteristics of a Zener diode. And here we have the voltage and current characteristics. In fact, it is a graph where on the x-axis we have the voltage and on the y-axis we have the current. The graph is divided into 4 quadrants. This is the first quadrant, then the second quadrant, and then the third quadrant, and then the fourth quadrant. The Zener diode will work either in the first quadrant or in the third quadrant. When the diode is working in the first quadrant, it will be forward biased, and the diode will act like your normal diode. If the Zener diode is made up of silicon, then the forward biased Zener diode will present a barrier voltage of 0.7 volts. And if the Zener diode is made up of germanium material, then the forward biased Zener diode will produce a barrier potential of 0.3 volts. And after the first quadrant, we see that the Zener diode is also working in the third quadrant. And this is the quadrant where all the Zener activity is happening. In fact, the Zener diodes are intended to be used in the third quadrant where the Zener diodes are reverse bias. In the reverse bias, we see that the graph, as the voltage in the reverse polarity increases, the current initially remains very small, very small. Then after one point, which is called the knee point, or which is also called the breakdown point, the graph takes a sharp turn and the current increases in the opposite direction rapidly. This is a place where we say that the reverse breakdown voltage has occurred. So the reverse breakdown, this term, the reverse breakdown voltage is actually happening at Vz, or the breakdown. And this reverse breakdown voltage is the feature added in the Zener diode. Although we have reverse breakdown voltages in our normal diodes, but those reverse breakdown voltage occur at a very large voltage. The Zener diode is constructed so that the reverse breakdown voltage can be controlled, and it is represented as Vz. This is also called the knee voltage, the breakdown voltage, and also it is also called the Zener voltage. The Zener voltage is also the breakdown voltage. Now we must maintain a certain amount of current, which is called the knee current, so as to establish the Zener voltage. On the y-axis, in the third quadrant, IZK, the term IZK represents the Zener knee current. It is the essential and mandatory reverse bias current essentially required to maintain Zener voltage. And then there is IZM, which is the Zener maximum current. And the region between IZK and IZM, or this region which is shaded, called the Zener diodes reverse breakdown region. And the Zener diode operates normally inside the shaded area, or inside the reverse breakdown region. This region is the place where all the Zener activity will happen, and it is the reason why Zener diodes are used. So Zener diodes, so just to summarize this slide, Zener diodes, they can act in the forward bias condition and they can also act in the reverse bias condition. But the intention of using a Zener diode is not to employ the Zener diode in forward bias condition. Rather, we should use the Zener diode in reverse bias condition. Now we come to the next slide. So the next slide is basically a guideline for the correct configuration of Zener diode connection. Remember that the Zener diode operates in both first quadrant and third quadrant. So in this slide, we see two diagrams which look almost the same, except that the direction of the Zener diode are opposite. In this circuit, we have a DC input voltage, we have a resistor R, and then we have a diode, which is here a Zener diode, and a variable resistance RL. In this circuit, although we are using a Zener diode, but this is not the purpose of using a Zener diode. Although in this circuit, let us assume that V in is larger than V of barrier potential of the diode. Then what will happen? We will have a current flowing, and this current will be the bias current. And if we take this Zener diode to be practical or of silicon material, then the VD in such case will be 0.6 0.7 volts, and the voltage appearing across resistance R will be Vin minus 0.7 volts. So in this circuit, what we have achieved is that we have got a forward bias current, but we did not get Zener voltage because due to one reason that we did not connect the Zener diode in the correct configuration. So therefore, if we need a forward bias current, then the normal diode would have been enough. Then we do not require the services of a Zener diode. So in this circuit, the Zener diode is forward biased and the output voltage is equal to 0.3 or 0.7 volts. The Zener diodes are not meant to be used like a normal diode. Then what is the correct configuration of a Zener diode? It is shown in the second diagram, the Zener diode reverse biased, or when the Zener diode is reverse biased. So let us first look at this diagram. We have a Vin, this is our external power supply, then we have a resistance, and then we have the same Zener diode, but this time the Zener diode is reverse biased such that the anode terminal is connected to the ground and the cathode terminal is connected to the output of the resistance. Whereas if we look at our previous diagram, what we did was that the diode in the forward bias condition, the anode terminal of the diode is connected to the output resistance of the terminal R, and the cathode terminal of the Zener diode is connected to the ground, which makes it forward bias. However, in the second diagram, the cathode terminal this time is connected to the output of R, and most importantly, the anode terminal is connected to the ground, which makes this configuration reverse biased. And if we take that Vin, the input voltage, is larger than Vz of the Zener diode being used, then we will get a V output equal to Vz, And this is the correct polarity configuration connection of a Zener diode. The Zener diode is reverse bias and the output voltage is equal to the Zener breakdown voltage of Zener diode being used. So whatever value of Zener diode we are using, the output will be equal to the same Zener diode provided input voltage is larger than Vz. Input voltage is larger than Zener breakdown voltage. So in this slide, we have learned two things. First, we have learned the correct configuration of the Zener diode, and secondly, we have learned that it is important to identify the terminals of the Zener diode. We cannot just randomly connect the Zener diode in our circuit and expect output voltage will be equal to V Zener. No, we have to first identify the terminals of Zener diode and then connect the Zener diode in the reverse bias condition. Only then we will get the proper functioning of the Zener diode.
Excuse me, sir. Sir, what are the IV characteristics of Zener diode?
Well, this is what I had shown in an earlier slide. These are the VI characteristics of the Zener diode.
Sir, can you explain it a little bit more?
So here in this diagram, what we see is the VI characteristics of a Zener diode. On the x-axis, we have the voltage across the Zener diode, and on the y-axis, we have the Zener current. The Zener diode works in either the first quadrant or in the second quadrant. When the diode is working in the first quadrant, it is called forward biased. And if the diode is made up of silicon material, then the forward bias voltage drop will be 0.7 volts. And if the material being used is of germanium, in that case, the forward bias voltage drop of Zener diode will be 0.3 volts. So the Zener diode can act like a normal diode when it is working in the first quadrant. The purpose of using a Zener diode is demonstrated in quadrant number 3. In the third quadrant, the Zener diode is reverse biased, and we see that in the as the reverse bias voltage increases, the current maintains a very minimal value. But after we achieve the breakdown voltage, the curve follows a very sharp negative slope. This is the function that we want to achieve from a Zener diode. And this graph has to be maintained by at least providing a minimum current of IZK available over here. And this is called the Zener knee current. This knee current represents the point where the Zener diode will produce output voltage equal to Vz. And now if we increase the output voltage from the source, the voltage of the Zener diode will be fixed across Vz or very close to Vz. So now we can increase the voltage of the external source, but the voltage of the Zener diode will remain constant and we will get constant output voltage. In this graph, IZK represents the knee current, IZM represents the maximum current that the Zener diode can allow, whereas the IZ, the term Zener test current, only represents our load current. It is the current which our Zener diode will be consuming at a certain time. And this region, the shaded region, represents the reverse breakdown region. And it is important that we work the Zener diode within this region. It is important to keep the Zener diode inside this region. Otherwise, we will get
Make a
unexpected
using a
results.
diode.
Can you repeat your question? I was unable with that.
Sir, can we make a regulator, voltage regulator using one Zener diode only?
Yes, we can. In fact, in a later slide, we will see how we will get a voltage regulator from a single Zener diode.
सर एज ए फॉरवर्ड बाइस जीनो डायोड को हम कहाँ कहाँ यूज़ करते हैं और एज ए रिवर्स बाइस हम जीनो डायोड को कहाँ कहाँ यूज़ करते हैं?
इसका जवाब ये है कि ये वोल्टेज रेफरेंस में काम आएगा एंड इन वोल्टेज रेगुलेटर्स. सो वोल्टेज रेफरेंसेस and also voltage regulators. This is second last line and the last line. Most of the time the Zener diode is used as a voltage reference. For regulators or for power supplies there are specialized circuits. Zener diodes when being used as regulators will supply a limited amount of current. Of course we can use Zener diodes in voltage regulators. It is one of their features, it is one of their applications. In the next slide, we have the Zener diode regulator. Zener diodes can be used to produce a stabilized output with low ripple under varying load conditions. By connecting a simple Zener diode in the circuit as shown below, across the output, a more stable output can be produced. So in this diagram, what we have is that we have a DC input voltage from rectifier or smoothing circuit. What is a smoothing circuit? It is our filter, output of the filter, which provides a DC voltage of even smoother value. So we do not have half wave pulsed or pulsed DC. We have connected a capacitor and we have achieved a smoothing circuit. But this smoothing circuit has a large voltage, but our load requires a little bit smaller voltage, but a well-maintained voltage, that it should not increase or decrease. And this voltage regulation in our case will be achieved using a Zener diode. Therefore, Zener diodes can be used to produce a stabilized output with low ripple under varying load conditions. So now if we change the value of RL over here, if we change the value of RL, when the current changes, the output voltage appearing across RL will not change. It will remain stable. So by connecting a simple Zener circuit as shown below across the output. So we have to use the reverse bias Zener diode directly across the output load. And what we will get is a more stable output voltage, that is by changing the value of R or by changing the amount of current, the output will not be affected. and we will get a constant voltage. Okay, ji, so next is by passing a small current through the diode from a voltage source via a stable current limiting resistance Rs, the Zener diode will conduct sufficient current to maintain a voltage drop of Vout. In this paragraph, what we have learned is that in order to use a Zener diode, we need a limiting resistance called Rs. This limiting resistance will always produce a suitable limiting current, which is essential for the production of output voltage. The resistance Rs is connected in series with the Zener diode to limit the current flow through the diode with the voltage source, Vs. And finally, the stabilized output voltage Vout is taken across the Zener diode. So in this circuit, what we have is we have one externally available power supply called Vs, such that Vs is much larger than Vz. Vz represents the breakdown voltage of the Zener diode. Once this condition is fulfilled, we connect a limiting resistance Rs. This Rs is essential in this circuit as it will consume the leftover voltage, that is Rs, that is Vrs. Voltage across Rs will be equal to Vs, the source voltage, minus the Zener voltage. And if we do not use Rs, then there will be no place to consume or to drop this voltage. And the Zener diode will not work if we do not connect Rs. So the series resistance is an essential part of the circuit. And now we will conduct a very simple experiment for voltage regulation. And in this experiment, we will discuss that as we change the input source voltage, then how will the Zener diode correspond? So let us discuss the circuit first. We have a variable output power supply Vs. This variable power supply is external and the voltage can be changed from 0 to 10 volts. Then we have a resistance Rs. This is a series resistance and it will limit the current flowing into the Zener diode. And then we have a Zener diode having model number 1N4733A. Now this 1N4733A represents the part number of the Zener diode being used, and we will find the voltage of such model from the data sheet as provided by the manufacturer. So if I can just go a little bit ahead of my slides. So here we have the data sheet of the manufacturer, and here we have the model number 1N4733A, and the voltage produced by this is 5.1 volts. So from the data sheet as provided from the manufacturer, the model number 1N4733A will produce a output voltage of 5.1 volts. This means that the Zener diode that we are using will experience a Zener voltage breakdown at 5.1 volts. Let's return to our experiment. So our input voltage supply is variable from 0 to 10 volts, and at one time it will cross 5 volts. So we want to see what will happen. And next we have a graph. This graph on the x-axis has the Vs, that is the input power supply, and on the y-axis we have the Vz, that is the output as produced by the Zener diode. So in this experiment, what we will do is that we will change the value of the input voltage and we will observe the output voltage across the Zener diode. And this is what will happen. So initially we provide 0 volts and we get 0 volts. And then we provide 1 volt as the power supply. So we provide 1 volt over here and we observe that output is also 1 volt. Now, why is the output also 1 volt? The output is equal to 1 volt because if we look back to the VI characteristics, we observe that before the breakdown voltage, the current flowing in the reverse direction of the Zener diode is very small. It will be in microampere. It will be so small that we can ignore the current. Therefore, we say that the current is zero until the knee voltage or the breakdown voltage or the Zener voltage. For this reason, what we have is that until we get the Zener voltage, all voltages will be available across the output because we do not have any current flowing in the circuit. And if we have zero current in the circuit, then there will be zero voltage across RS. That means that all of the input voltage provided will be available at the output. So as we increase the voltage from 0 volt to 4 volt, the same voltage will be available across the output. But then when we increase the voltage beyond 5 volt, when we increase the input voltage beyond 5 volts, then we do not observe any change in the output voltage. It is because that we are using model number 1N4733, which has a breakdown voltage of 5.1 volts. So this means that as the power supply Vs is increased from 5 volt up to 10 volt, the output voltage will remain fixed. It will be locked to 5 volts. And this is the voltage regulation. So now if we change the output voltage, anywhere between 5 volts to 10 volts, the output voltage will be regulated. And this is the application of the Zener diode.
सर सिंपल डायोड की कॉन्फ़िगरेशन को कुछ ऐसा बना दें कि वो भी वोल्टेज रेगुलेटर के तौर पर काम करे, तो क्या चेंजेस करनी पड़ेंगी उसकी IV करैक्टरिस्टिक्स?
नहीं, वो आप नहीं कर सकते बिकॉज कॉन्फ़िगरेशंस या उसकी प्रॉपर्टीज जो उसका मैन्युफैक्चरर रख देता है उसको फिर हम डिस्टर्ब नहीं कर सकते जी। नेक्स्ट क्वेश्चन।
सर अगर इसके थ्रू एसी वोल्टेज दिया जाए तो सर ये अगर रिवर्स बायस वोल्टेज को तो फिर ये से फॉरवर्ड बायस की तरह चलाएगा ना, तो इट विल एक्ट एज अ रेक्टिफायर समवट रिपलिंग वोल्टेज।
Now if we replace the DC input power supply by a AC signal, then our output voltage will look like this. That is, as long as the input voltage is smaller than Vz, we will have the same voltage. When the input becomes larger than Vz, we will have an output voltage equal to Vz. And when the same input voltage decreases less than Vz, the output voltage will follow. Now, what will happen during the negative half? In the negative half, the Zener diode will be forward biased. Therefore, the output will be equal to 0.7 volt from pi to.
So why is that? It's 0.7 volt. But sir, when it reaches negative peak, wouldn't it be positive peak over the output?
It is so because when we use the signal in the negative half, the Zener diode becomes forward biased. And a forward biased PN junction always produces 0.7 volt in case of silicon or 0.3 volt in case of germanium. So yes, we can use a Zener diode in AC cases, but in that case, our output will be clipped at a certain voltage level as defined by the value of Zener volt. हाँ जी पूछें।
सर ये नेगेटिव पीक के ऊपर 0.7 वोल्ट इसी वजह से रहेगा क्योंकि वोल्ट डायोड का वर्किंग वोल्टेज 0.7 है।
नेगेटिव मोड की आप बात कर रहे हैं?
यस सर, नेगेटिव पीक की बात कर रहा हूँ मैं।
ये नेगेटिव यानी कि इस ये जो नेगेटिव पीक है यहाँ पे?
यस सर, इस पीक के ऊपर आप कह रहे हैं 0.7 वोल्ट आएगा डायोड के अक्रॉस, हालांकि पीक नेगेटिव मैक्सिमम पीक है। सर डायोड 0.7 क्यों दे रहा है? हमने कहीं ग्राउंड वगैरह तो नहीं लगाया हुआ?
Because if we look at it like this, the polarity has been reversed. इस बात को हम मानते हैं कि नेगेटिव हाफ में आपने पोलैरिटी रिवर्स कर दी है।
यस सर। ठीक है,
ओके। Now the voltage is minus V peak, ठीक है, corresponding to this point. Here we have, ठीक है, now this terminal is positive and this terminal is negative. Polarity as shown. So अगर आप if we analyze this circuit, our diode is forward biased, and when we have a forward biased diode, what will happen? Current will start to flow like this, and not only current will flow, the voltage appearing across the forward biased diode will be 0.7 volt. Or to be more precise, the voltage will be VZ in this case will be minus 0.7 volts.
क्यों सर बाकी वोल्टेज ड्रॉप RS के क्रॉस होगा?
And the remaining will be available across RS. So in this example, where we have connected a sine wave, what have we achieved is that we have changed the wave shape of the input signal. That is, we have now changed from a sine wave to a half wave and also clipped away a certain part of the input voltage. Okay? As I'm going to finish this class, and we will meet in the next class, inshallah. So please everybody, all the class, all my students, please read from the textbook, and inshallah next time we will discuss a new article. Thank you very much. Assalamu alaikum.
Sir, kindly share the slides.
हाँ जी ठीक है जी.